So in this video, I want to show you how I apply quaternions to John Mackin's electron model. Now, you may remember many videos back, I was starting to review a paper of John Mackin's research into his ether model, and in particular his electron model. And so this is the reason I've been flogging the dead horse of the quaternions, why I've been pushing the quaternions in these videos, is because I want you to understand them the way I understand them, so that you would better understand John Mackin's electron model, the model, how I use quaternions to generate his electron model. So as I said in the previous review, the previous video I made of John Mackin's paper, I think his research, his ether model, is the closest to the truth of anyone else I've studied up to this point. Okay, I think his ether model, basically, I believe there can be an ether, I believe there is an ether, but I also believe there can be an ether. It may not be able to be provable in a absolute sense, but I believe there can be an ether, and I believe that this model that John is presenting is the closest to the truth in terms of how the model maps out. So he recently sent me his latest paper, Oscillating Space-Time, the Foundation of the Universe. And this is basically a remake of his previous paper, only he told me he got feedback from a bunch of people, from some students that he was working with. He wanted to see if his students, the students he was working with, were understanding his theory the way he intended. And through his conversation with these students, he rewrote his paper to be more articulate. And so I haven't read the whole paper yet. I started reading it, and it's quite good. John is a very good writer, and he articulates his ideas very well. And so I'll just read this, the abstract of this paper, just to remind you of what his theory is all about. Okay, so, and this paper has been accepted for publication by the Journal of Modern Physics. So this will be officially published. So it was peer-reviewed, and it will be published. So in this article, space-time is modeled as a quantum mechanical sonic medium consisting of Planck length oscillations at Planck frequency. Okay, so I like this idea. I like this idea because Planck frequency is an extremely high frequency. It is higher than any frequency that we have ever perceived in our lifetime, and it is, to me, Planck frequency is analogous to the clock frequency of a computer. So as you may know, if you know anything about computers, the CPU is run off a clock, and the clock is usually, it used to be megahertz and now it's gigahertz. The clock frequency of the computer is what drives the computer, basically. It's what coordinates all of the processes in the computer. And so if there was no CPU, if there was no clock, if there was no computer clock, then computers could not run. Computers run off a clock, and that is how I see Planck frequency. Okay, so I like this idea. Planck Planck length time oscillations give space-time its physical constant, C, G, and H bar. He uses H bar. I prefer H. I had previously did some number crunching to convert everything to H, and I know I can convert his language to using H instead of H bar if I want to. And so he uses H bar because he's calibrated to the radian, and when I use H, I'm calibrated to the clock. I'm calibrated to the cycle. Okay, so that's the only difference I see between what John is saying and what I would say if I were writing this paper. Okay, so oscillating space-time is proposed to be the single universal field that generates and unifies everything in the universe. The 17 fields of quantum field theory are modeled as lower frequency resonances of oscillating space-time, so lower than Planck frequency. A model of an electron is proposed to be a rotating soliton wave in this medium. An electron appears to have wave-particle duality, even though it is fundamentally a quantized wave. This soliton wave can momentarily be smaller than a proton in high-energy collisions, or have a relatively large volume in the atom's orbital wave function. Finding an electron causes it to undergo superluminal collapse to a smaller wave size. This gives an electron a particle-like properties when detected. And I have different ideas on this, but I won't get into it right now. So the proposed wave-based electron model is tested and shown to have an electron's approximate energy, the de Broglie wave properties, and undetectable volume. Most important, this electron model is shown to also generate an electron's electrostatic and gravitational forces. The gravitational properties are derived from the nonlinearity of this medium. So the medium is basically responsible for the properties of the electron. When an electron's gravitational and electrostatic forces are modeled as distortions of the soliton waves, the equations become quite simple, and a clear connection emerges between these forces. For example, the gravitational force between two Planck masses equals the electrostatic force between two Planck charges. Both the force and the magnitude are equal to hc over r squared. Okay, so that's his abstract. The paper is quite long. It is, I think, 35 pages long, something like that. And so we're not going to read the whole paper. Really, what I want to show you is how I apply Quaternions, the Quaternions that I've been presenting to you over the last several videos, how I can apply that to generate John Mackin's electron model. So in a previous video, I showed you how I use Quaternions to rotate a bunch of points around an arbitrary axis. In this case, actually, so here, positive x is to the right, positive y is up, and positive z is into and out of the page. And right now, I am spinning counterclockwise about the vertical y-axis. Okay, so I showed you how I used Quaternions, and then I gave you some code in the P5JS format to do the same thing. Okay, so this is quite straightforward. Only in order to accomplish this, you need to apply two operations. You need to apply the Quaternion rotation, half of the Quaternion rotation with a where you post multiply the point, and then you have to apply the complex conjugate and pre-multiply the output of the first Quaternion. And so that is what I'm showing here. So you set up your initial point, which is the center of the sphere. You set it up in a vector like this, if you want to call it a vector, or a 1x4 matrix like this. Then you multiply, you take the transformation matrix and you multiply the point, and then you take the output of that and then you multiply that by the complex conjugate and you get your output point. And that is how we are able to spin the points about an axis. It doesn't have to be a vertical axis, it can be an arbitrary axis, but in this case it is the vertical axis. So you'll see here when I point the y-axis towards the screen, you can see that we are spinning counterclockwise about the y-axis. So here's the code that I showed in the previous video, where we set up the point. I actually put the point into a Quaternion matrix. Now this is overkill. I know this is overkill. The point doesn't have to be a 4x4 matrix. It could actually just be a 1x4 matrix. But I'm doing this for simplicity so my code looks better. It is not the most efficient way to do it. I agree. But I can set up the point as a matrix, as a Quaternion matrix. I can set up then I multiply the point with the rotation matrix, which I'm setting up here. Then I get out a temporary matrix, a temporary point. Okay, this is the new point. and then I pre-multiply it by the quaternion matrix, the complex conjugate. This is the conjugate, and I get my final result. Okay, so this is how, if you want to do rotations where you don't get any weird effects like the compressing effect that I showed you in the previous video, then you have to do it in 2 parts. It does not work if you do it in 1 part. But what we're going to do here is I'm going to change my code, and I'm going to rebuild it here. I'm going to change my code so that we are only using 1 quaternion and 1 quaternion operation, 1 matrix, 1 rotation operation, and we're putting in the whole angle. Okay, so when we do that, we get the strange effect where the points converge to the middle. Okay, we get the strange effect where, as I'm rotating, the spheres are being compressed to the middle, and then they're being uncompressed. They're being compressed and uncompressed towards the plane in the middle of the axis of rotation. Okay, so here is my axis of rotation here. I'm going to kind of bring this up to the middle so you can see y is the axis that we're rotating against. And when we only look at the xz plane with the y pointing towards out of the screen towards me, it looks like a counterclockwise rotation, but you can see that the points are turning gray and black and white and gray and black and white, and that is because I am painting the spheres. Let me get this out of the way. Okay, I am painting the spheres based on whether they're up or down. So spheres that are up are painted white, and spheres that are down are painted black. And you can see that we get this weird effect where they collapse to the middle and then come back out again. So this is the effect we're trying to avoid when we do the 2-step, the quaternion times the point, and then the new point times the complex conjugate. This is the effect that we're trying to avoid. Okay, this is not what we want when we want to rotate points about an arbitrary axis. Okay? So to try and understand this a little better, what I did was, instead of using a bunch of random points that were just scattered around the origin, here what I did was I generated a sine wave. Okay, and so now I can spin the sine wave, and you can see that it is spinning. You can see it's going into and out of the page. And so when we try to look at that like this, so now I have I'm spinning about the y-axis, so now I have the y-axis pointing towards me, and you can see that I'm doing a counterclockwise rotation of the sine wave about the origin of the y, about the y-axis. Okay, and so the y-axis is now into and out of the page. And so, like, let's put this back so you can see the sine wave, and you can see I'm spinning it. As I spin it, the white is going into the page, and it's to the left now, and now it's out of the page. It's really hard to see. And then as I spin it, it goes to the right, and then the white goes to the back. Okay, so you can see I'm just spinning the sine wave about the y-axis. So now we're going to do the whole angle with the single operation using the whole angle, and we're going to disable the half angle operation. Okay, so here is the sine wave, and now we're going to apply the spin. We're going to apply the Quaternion operator, the rotation operator, to the sine wave, and we're going to do it at 10 degrees at a time, and you will see that it is basically shrinking. And now what we have here is we have we have the sine wave is now just a line. Okay, the sine wave has collapsed to the origin, and it is now a line. So now what I'm going to do, I'm going to leave it a little off center like this so you can see. I'm going to keep going, and now we're getting the sine wave back, and after 90 degrees now we've got the sine wave back. So every 90 degrees now we are getting this collapse to a line, and then after 90 degrees we get the full sine wave back. Okay, so if the goal was to rotate a sine wave about an arbitrary axis or a y-axis or some axis, this is not going to do the job. This is not going to do anything interesting whatsoever. We're not going to be happy with this. Okay, but it kind of got me thinking that maybe there is a use for this functionality because it's so simple, because it's just plug in the angle, apply the Quaternion rotation matrix, and something happens. Because this is so simple, it got me thinking that maybe this is something that nature does, that maybe this is something that that nature uses. And, of course, I'm looking for the math that nature uses. I don't really care about the math that humans use to do rotations in three-dimensional space. I know how to do that. I have to do it in 2 steps using Quaternions. There is no other way. But is there a use for this functionality? And it took me a while to figure it out, but one night I was lying in bed, sleepless, trying to fall asleep, and I couldn't, and so I started wondering what I could use this for, and then I saw it in my head. I figured out how I could use this to create something that I had seen before. So what I did was I took the original sine wave that I had generated and I spun the sine wave, but I spun the sine wave using the whole angle single step flawed Quaternion method. I took the sine wave and then I got this shape right here. Okay, and this is in fact the electron model that John Mackin came up with. Okay, this is exactly the geometry of the electron model that John Mackin is showing in his paper. So I'm talking about this model right here. Okay, this is the John Mackin's electron model. This is a graph of it sort of looking straight down as if it's rotating a clock. And this is what this sine wave looks like when you look at it face down on here. I'm going to shrink this down a little bit so you can see it better. So this is what, this is exactly the model that John Mackin is using for his soliton electron wave standing wave model. So here is that figure on the left, and here is my model, which I colored to be kind of similar to his model. I colored it that this is a bluish color and this is a yellowish color. And so you can clearly see that this is exactly his model. And so let's just go to this next slide here. Here it is in black and white. I think it looks better when the colors match more closely to his model. Okay, so here is just his figure here, which I am depicting here on the right. Okay, but and here it is. Here's an animation I did of this model, his model spinning. Now mine is spinning counterclockwise, and he shows his spinning clockwise, but my Quaternions naturally spin counterclockwise, and so that is why this one's spinning counterclockwise. So this is his model. This is an animation of his model spinning, and that is what he's trying to depict in his figure right here. So here he shows this model. Here he shows what it looks like spinning, and I am showing his model and what it looks like spinning. Now, one other interesting thing I did was I imagined that I was trying to figure out what this would look like if it wasn't spinning. Okay, so I created this animation where I did the Quaternion spin to create the the whole angle quaternion spin to create the model, and then in my software I pretended that it wasn't spinning because I wanted to get this effect, and I'll show you what this looks like. So you get this sort of piston effect, and that's something I was seeing in my head. I was seeing this sort of piston action. Yes, it's spinning, but is it really spinning? Like in space, this looks more like a quantum fluctuation. Now he refers to his his ether model as quantum fluctuations, and so it made me wonder if this couldn't also be the model for the quantum fluctuations that he talks about in his model. So this is what it looks like in my software when I actually do spin the object, but when I use the whole angle spinning for the model and not the half angle spinning. Using the half angle spinning, it's just going to spin, but using the whole angle spinning, now this is very slow because I'm spinning all these spheres. These are like volumetric spheres, not volumetric spheres, but it has to surface render all these spheres, and so that is why this is so slow. So I'm basically doing my rotation of the model using the whole angle quaternion, the one that makes it, so you can see how it expands during every 90 degrees. It expands to fullness, and then in 90 more degrees it contracts to become very flat. Now this is very slow and painful, which is why I made those animations. Okay, so let's see if I can get it back to being flat. Okay, one more. Okay, after 90 degrees, now we've got it flat as a pancake. And after 1, 2, 3, I'm going 10 degrees at a time. 4, 5, 6, 7, 8, 9. So after 90 degrees, now we have the fully expanded wave. So using the feature now, I'm going to call it a feature, using the feature of the Quaternion, using the whole angle and only doing one step, and instead of the half steps for the just rotating about a point, I'm able to generate, not only am I able to generate John Mackin's model, but I'm also able to generate this sort of piston action where, you know, it expands and then in the middle it's flat and then it expands again. This sort of piston action effect, which kind of looks like a quantum fluctuation. So that is why, this is why I'm so interested in Quaternions, because it can do so many things. And the 4x4 matrix version of Quaternions just helped me to understand Quaternions enough to be able to kind of imagine this kind of thing happening. And so I don't think I would have been able to come up with this if I didn't really understand Quaternions and how they work and how to use them in various different contexts. Okay, so here, okay, so to recap, I am able to generate John Mackin's model of the electron using Quaternions, only I'm using Quaternions in a non-standard way where that is used in computer graphics to rotate objects around an origin. I am using the non-standard way where I am using the whole angle and only in applying the one Quaternion and not the complex conjugate, and I'm able to get I'm able to produce John Mackin's model. Okay, so I thought that was really interesting and I wanted to share that with you. I've been wanting to make this for a while, but I really want to pin down the Quaternion. I want you to understand the Quaternions the way I understand them so that you can have a better understanding of what is going on here. Okay, so I will leave a link to John's paper in the description. I think you know, I think it would be a really good idea for everyone to read that if you're interested, and I think you should probably read that paper. Again, I'm not done reading it myself. I'm in the middle of it, and so I'm still working on it. And when I find something interesting, I will let you know. All right, so yeah, I will be back soon.